Any more announcement? Well, so then we're going to continue with planet formation that we started yesterday. So please, Jeff.
Very good. Thank you, Isa. Now, just to go through this again, we have observations that we use for our planet formation models, and most of them are from the solar system. There are some from circumstellar disks, and that includes the chemical aspects that Ted was discussing somewhat this morning, and I think we'll finish up talking about tomorrow morning, and physical aspects, extrasolar planets, and I will summarize those assumptions today, but then I'll go into much more detail about them tomorrow. And I just want to give you this lecture because it feeds into David's lecture, which is coming up after the coffee break. Then, bulk of the talk will be solar nebula and planetesimals, the growth of planets within disks, basically. And I'll talk a little bit about the disks themselves, but I'll focus in on solid growth, and I'll also talk a little bit about volatile delivery to the terrestrial planets, although David is going to elaborate on some aspects of that in his talk. And then I'm going to talk a bit about the accumulation of the gaseous envelopes of the giant planets. This cartoon, which I talked about the artistic aspects yesterday, this is a planet. It's a proto-giant planet. It's mostly rocky now, and it has a bit of an envelope, an atmosphere that it's starting to accrete, and it's clearing a gap around itself. It's just starting, and it's affecting also particles, especially right nearby, and perturbing streamlines and changing the pattern of flow in the disk. I went over these yesterday, but quickly. Dynamics, planets, orbits are nearly circular and nearly in the same plane. So roughly geometric distance, so the fractional distance increase is roughly constant from planet to planet. Asteroid belt is a gap there where something may have been and was thrown out. The giant planets all have satellite systems, and those are moons farther out, but right near the planet where the tidal forces are too great, you have just smaller bodies which organize themselves into flattened disks, planetary rings. And planets rotate many times per orbit, except the Mercury and Venus, because they've been slowed by tides, so we don't know really much about their original rotation. Composition, and the gross properties. The large bodies, Jupiter and Saturn, are the most gas-rich. You have Uranus, Neptune, kind of intermediate, and the bodies smaller than those are essentially all condensed matter, very little hydrogen, helium. And among the condensed matter bodies, they're essentially rocky, close to the sun, Mars and inward, icy, far from the sun, Jupiter and outward. Jupiter's inner satellite, Io, is an exception because it is rocky. The asteroids tend to be rocky, but many of them actually have up to 20 or 25% ice, water ice. And farther out, typically half water ice for the bodies where we have mass estimates. And then the meteorites I showed pictures of show that compositions are very similar, aside from the volatiles, some of which did not condense or condensed at one part of the solar system, but not and the other part. But if you look at them physically, the structure of meteorites imply vast, complex processes. And then if we look at planetary surfaces, we see that the 4+ billion year old, 4.5 billion, 4.4 billion year old surfaces like the lunar highlands are very heavily cratered. The somewhat younger surfaces like 3.5 billion years, the lunar maria, have maybe 1% as much crater. So there's a lot more stuff during that billion-year period from the formation of the highlands to the formation of the maria. Constraints from meteorites, very accurate dating of the solar system. And this is from these Concordia dates of various different radiogenic decay products that Ted was talking about yesterday morning. Precision is about 1 million years, and that is less than 0.1% uncertainty. The oldest things are these very high temperature calcium aluminum inclusions, which are a few millimeter to centimeter size, very refractory things found in some of the most primitive meteorites. Accretion occurred rapidly. This is 4,500 million years ago. And the primitive meteorites, we see some diversity in age, but it's less than 5 million years. So 0.1% of the age of the solar system, or less, was the epoch of growth of solid bodies. Some differentiated meteorites. Differentiated means that they were in a body that got hot enough that there's large-scale melting, and the heavier things sunk to the center. Basically, iron and elements and compounds that are chemically compatible with iron. Uranium is very, very dense, but it combines with oxygen. It is not chemically good match for iron. So even though it's very low, very high density by itself, it turns out it gets very concentrated in the crust of a differentiated body, not in the interior. And the amount of differentiation depends on the temperature and the pressure at which it occurs, but basically the major constituents are silicates and metals. So iron and iron-loving things sink because as a group they are denser than the silicates by a significant amount. If we look at the microstructure chemically, we look at meteorite compositions, aside from the volatiles, for primitive meteorites, not differentiated ones where the iron falls down, the silicates go up, and different elements are compatible with one or the other. But primitive bodies, you get very similar compositions from one to another apart from the volatiles. Different temperatures at which their constituents condensed means different levels of depletion of the lower vaporization temperature, lower condensation temperature constituents. In this active processing, the chondrules, which are little igneous inclusions, and they are a mix of elements, but they're formed from flash heating and cooling to temperatures of 1500 or so Kelvin. Now with the giant planets, We look and see, we can estimate the heavy element constituents of the giant planets, and the total heavy elements is the blue. The part that is in the core is the red. And we have pretty good ideas for Uranus and Neptune because the heavy elements make up most of those constituencies. Saturn, there's a bigger uncertainty, and whether it's in the core or a lot of it is spread out through the envelope is also uncertain. Jupiter, even higher uncertainties. And the reason for this is Jupiter is roughly 90% hydrogen, helium, and small uncertainties in the equation of state at megabar pressures, which are not accessible in the lab. They're not that well known, and little bit of uncertainty, little small fractional uncertainties of dominant constituents, their density at a given pressure, translate into large uncertainties in these trace constituents, the fractional abundance of the trace constituents. And don't even have direct evidence of whether any of these trace constituents, these heavy elements, maybe a little more than trace constituents, but at least a few percent, and maybe a little over 10% of Jupiter's by mass. It's not certain how much is in the core, because Jupiter is definitely not very gravitationally condensed compared to what you get just by the pressure effect on a homogeneous chemical mixture. Solar system constraints, as I said before, flat, orbiting in the direction of solar spin, low eccentricity. Near the plane of the sun's equator, really about 7 degrees off, which is somewhat of a mystery, but roughly that's close to the plane. And the inclination of planetary orbits relative to one another is generally a few degrees or less, a little more for Mercury, it's 7 degrees, and a bit more for some of the small objects. Most of the spins of planets are in the same direction of their orbits in the solar spin, prograde, and most of them, the rotation axis is roughly parallel to the orbital angular momentum. Not too large an angle, 23 degrees on Earth. Primitive meteorite ages, moon rock ages, stop at about 4.45, 4.46 gigayears. And the moon is a fairly small body, so lunar formation is probably not much before this time. That's, you compare 4.45 to 4.56, and you say, oh, well, it's about the same time, but that's a little over 100 million years. Earth rocks are less than about 4 billion years old. There are zircons, these little grains that are very hardy that Ted talked about yesterday, which are 4.3 or so billion years old, maybe 4.4. Largest planets are most gas-rich. Asteroid belts, small objects, total mass less than 100th that of Earth, well under 100th out of Earth, around 1,000th. Kuiper belt is a larger version, icier version of the asteroid belt in many respects, out beyond the orbit of Neptune. And there's also a concentration of asteroids at the in the orbit, sharing the orbit with Jupiter at the triangular points where they're dynamically stable for long times, and of Neptune. The only other location in the solar system where there's a substantial stable region in heliocentric orbit that isn't occupied is inside the orbit of Mercury. And then the Oort cloud, which is the source of many of the long period comets like Halley's Comet, dynamically new comets, and that's much farther away. It's a distribution that's from mostly 10,000 astronomical units, the Earth-Sun distance, to 50 or so thousand astronomical units. And objects are thought to have been tossed out there. They're bona fide solar system objects. As comets come in, they're going much less rapidly than interstellar bodies. As we know, the typical velocity of a star relative to the sun is about 30 kilometers a second. And the orbits of the parabolic comets are within 100 meters per second of parabolic. Most of them are, before they come into the planetary zone, look like they're slightly bound to the solar system, in other words, elliptical, with a very large eccentricity. In a few cases, the orbits seem like they're slightly unbound, but they're very slightly unbound. And this is probably either slight errors in the observations or that there have been some non-gravitational forces. Comets, they release volatiles. This causes kind of a jet coming out from them. It's like a rocket exhaust, pushes them one way, and the rest of the body goes the other way. Going into a little more detail, satellite systems. You have these what's called regular systems, perfectly well ordered in their orbital plane, nearly circular, fairly well spaced, just like the planets. The rings on the inside. Then a little farther out, there are small moons, and then there tend to be larger moons. Occasionally, there's some mixing around, but certainly, oops. Let's see. Yeah. Between the rings, there's some moons interspersed with rings, but they tend to be very small moons. And small moons mean small enough that their physical coherence matters and allows them to be held together, even though the fluid body of their density would be tidally ripped apart at the location. Then there are more distant moons of the giant planets. All four of them have dozens of these now, or well, dozens of for Jupiter and Saturn, and as many medium-sized ones for Uranus and Neptune. You can't see the smallest ones. These things are typically hundreds of planetary radii away, much farther than the regular inner satellites, and they're on highly eccentric and inclined orbits. They seem to be, the regular satellites seem to be formed in a nice calm disk. The irregular satellites seem to be captured objects from probably planetesimals in the circumsolar disk, the protoplanetary nebula. You look at meteorites and these little microstructures, the chondrules and CAIs I mentioned, heated to very high temperatures, but both from their physical structure, glass cooling very rapidly as opposed to being crystallized, and the fact that they're depleted in volatiles, but they're not, in many cases, they have a little bit of things that condense at, or boil off at 1,000 degrees Kelvin, somewhat more of things that boil off at 1,200 Kelvin, and a full relative abundance of things that go up to 1,500 Kelvin. And to do that, you have to go very quickly through, because they weren't at a very long, they couldn't have been hotter than 1,000 Kelvin for very long, but they certainly got hotter than 1,200 for a little while, and then they made it up to 1,500 because that part got melted. So they had to be heated and cooled very quickly, because in equilibrium, hot enough to melt the silicates, things like sodium will completely evaporate from these small bodies very quickly. There's nearly isotopic uniformity, other than the isotope ratios are nearly uniform. There are exceptions from the decay of radioactive elements from parents that were chemically different that Ted was talking about earlier, but there are also some small things that can't be explained by this, and they imply that some interstellar grains made it into these bodies without having vaporized. And when I say some things that are really irregular and require that, you have some grains that have this called neon E, exotic neon isotope ratio. And neon's a noble gas. Most of the neon is neon 20, but certain type of carbon star produces sodium 22, which decays with a half-life of 2.6 years into neon 22. So in some outflow, some carbon grains from those stars, there was some sodium 22 that condensed, and then it decayed, so the was sodium 22 portion of it decayed into neon 22, and you see this high ratio of neon 22 to neon 20 in those grains. There's no way they could have vaporized subsequently. They've survived since they were formed from the outflow of the star. So not everything got hot enough. That's the key. Some of the small bodies are differentiated and melted, and you can tell that from the crystalline pattern of the rocks that formed in some of these differentiated meteorites, and structures that imply that they were under low pressure and low gravity when they solidified. Atmospheres. The giant planets are dominated by accreted gases, hydrogen and helium, which are not going to condense at any reasonable temperatures in the solar system or the protoplanetary disk. But then there's the terrestrial planets, are dominated by volatilized solids, things that were frozen out, accreted by the planets, and then vaporized. And the reason we know that, as opposed to just having a primordial atmosphere of accreted gases and then hydrogen and helium escaping because they are lighter, which is a possibility, is that if you had that, then you'd have much more of the noble gases, the heavier noble gases. Argon, krypton, xenon. Now, you might recall from yesterday that the third most abundant gas, almost 1% of the Earth's atmosphere, is indeed argon. Most of that argon is argon-40 from the decay of potassium-40 not argon-36, which is a cosmically much more abundant isotope. Planetary surface, I talked about the variations in amount of cratering, the rates of cratering, because you get surfaces which are 30% older but have 100 times as much crater density. And then if you look at the distribution of angular momentum in the solar system, whereas over 99.8% of the mass of the known solar system is in the sun, over 99% of the angular momentum is in the orbits of the planets. Now, that's not quite fair because the solar wind has been slowing the rotation of the sun. But when the sun was very young, even if it was rotating near breakup, it would still be only comparable to that in the planets today in terms of rotational angular momentum, and with 99.8% of the mass. I'll go into more details later on about this in my next lecture, but I want to summarize the clues from exoplanets. Sorry for not catching that earlier. About 1 in 200 sun-like stars have planets more massive than Saturn within 0.1 AU. These were relatively easy to detect. Many of the early planets discovered around other stars were these so-called hot Jupiters, and a lot of people think that they're the most common exoplanet. They're actually pretty unusual. Very small fraction of the stars have them. These giant planets are made primarily of hydrogen and helium. There are a few that are relatively metal rich, up to about half what we call metals, which is lithium and heavier, oxygen, etc. Astronomical nomenclature. And the models suggest it's really hard to form these planets right near their stars. They probably formed farther out and moved inward. I'll talk about that a little bit later on. About 7% of sun-like stars, roughly solar mass, have planets more massive than Jupiter within about 2 astronomical units, so closer than the inner edge of the asteroid belt. So these are a lot more common than the hot Jupiters, but still somewhat uncommon. And many of them have very eccentric orbits, highly non-circular. Less than 2% of the small stars, ones between about 1/4 of a solar mass and half a solar mass, the M dwarfs, and the smallest M dwarfs we don't know, but we think it's the same too. They're just very faint, so hard to observe, have planets more massive than Jupiter within 1 AU. I think it's around 1%, but there aren't many of them, so we don't have real good statistics. But they're certainly significantly less common than around sun-like stars. And slightly more massive stars tend to have more of these giant planets. Stars with higher metallicity, again, heavy elements, are more likely to host detectable giant planets, but not terrestrial planets. So it seems that solid material is necessary for giant planets, but not terrestrial planets. Well, that's not quite true, because the real old stars, which have very little solids, we don't have any information. But this is something that I'll be talking more about in terms of the metallicity in the next 2 lectures, because the Kepler data have given us the information for the terrestrial planets. Sorry about the contrast. This says stars with one detectable giant planet are more likely to host more detectable planets. And this is detectable with the radial velocity that's been used on many, many stars, on thousands of stars, not the really precise, which takes a lot of telescope time, that's been done just for a few dozen stars. More than a few percent of stars have roughly Jupiter companions within a factor of 2 of mass, roughly the same distance, but at least 20% don't. And it's a little difficult to get bounds because in the lower range of this distribution, something that's, say, a half a Jupiter mass, a little bit farther from Jupiter, we don't have that many stars where we can exclude those planets, because you need a long time of fairly precise radial velocity variation measurements. And then there's this thing called the brown dwarf desert. Jupiter mass planets are the most common giant planets. More massive planets get rarer and rarer. They do go up to over 10 Jupiter masses, but they're quite uncommon. And then things called brown dwarfs, which are massive enough that you can have fusion of deuterium, heavy hydrogen, but not fusion of common H1 isotope. They're about 13 Jupiter masses to about 75, 78 Jupiter masses. Then beyond that, you can have self-sustained fusion of common H1, and that means you have this long-term source of energy to balance the contraction and radiation, and you get main sequence stars. The brown dwarfs are kind of these intermediate mass objects, and there just aren't that many of them compared to near solar-like stars, compared to the number of giant planets and small stars. And that implies the fact that there's this kind of gap, pretty much, that if planets form the same way stellar companions, binary stars, formed, then you'd expect a fairly continuous distribution. So this desert, in terms of very few objects of this size orbiting near solar mass stars, has strong implications for formation possibilities, formation theories. With the smaller planets, those less massive than Neptune, some of them close in are actually a little physically larger, are far more common than giants, and the abundance of planets increases as size decreases down to at least 1.5 Earth radii. Probably smaller, but we don't have the data yet. And this is within about half an AU to 1 AU, because this is all Kepler stuff. About 20%, and it's transits, and we're operating for 4 years. We needed to get a few transits, 3 transits minimum, but if they're near the bottom end of the size range that we can detect, we need more to get a good enough signal to be confident it's real. About 20%, 1 in 5, sun-like stars have 1 or more planets larger than this size, 1.5 Earth radii, with orbital periods less than 100 days. Many of these stars have 2 or more such planets orbiting the same plane, so they both are observed to transit, or more, several are observed to transit. The abundance of smaller planets does not depend strongly on stellar mass or stellar metallicity. So with giant planets, the more metals the star has, either because it has more mass in general or because its metal to hydrogen ratio is larger, the greater chance it has of having a giant planet, but not of a terrestrial planet. We don't yet know how common Earth-like planets are. And this Eta Earth, the abundance of Earth-like planets, is all done by extrapolation. There's no direct data for sun-like stars. Planets of one Earth radius, and at about 1 year period around a sun-like star, we don't have any. There's some, closest one is about, well, 1.4 Earth radii around a star a little bit smaller than the sun, called Kepler-62, and that planet is Kepler-62f. So, the synthesis. Solar system, the metal content, the fraction of heavy elements decreases as planet size increases. Gas, well, rocks, gas giants are the largest, least heavy element rich. Ice giants, rocky bodies. Small exoplanets, and these are rock and ice if they're far enough from the sun, cold enough area. Small exoplanets are more common than large ones. It's a continuum in masses for planets, although there may be a little bit of a dip at about from bigger than 30 Earth masses. Somewhat of a, I don't know, it's not quite a desert, but parched area between about 30 Earth masses, but we don't, which is twice Uranus or Neptune, and a couple hundred. There's just, it doesn't increase as you go down, certainly. I'll show you a plot tomorrow about that. But these, and then as you get smaller, just a complete continuum. But above Jupiter mass, you go down, you go into this desert, and then go back up at stellar masses. All known exoplanets larger than 3 Earth radii, or all exoplanets with known densities, plus many smaller ones, contain substantial amounts of hydrogen, volumetrically substantial. In the case of 4 Earth radii, hydrogen is not dominant by mass in general. And there are a few giants must also contain substantial metals. Observable planets are more common, or giant planets are more common around higher metallicity stars. Diverse range of exoplanets. Systems like our own may be common because, although we haven't seen anything like our own, we haven't seen planets around a lot of stars. The majority of stars we have not seen planets around. And that's when you do the statistics and compensate for the fact that Kepler only sees them when they're edge on. So although Kepler's type systems of big planets close in, or moderately large, Earth, between Earth and Uranus size, close in, that's the most common planets that we see. They're around 20% of the stars or so. Now I'm going to go into the models. Solar nebula theory. This was originated by Immanuel Kant and independently and more mathematically by Pierre-Simon de Laplace. And these are people whose names you're probably familiar with from other fields. Kant was a natural philosopher, known for a general philosopher. Laplace was what we would call today a mathematical astrophysicist. And the idea is the planets formed in a disk that was in orbit around the sun. It explains the near coplanarity and circularity of the planetary orbits. That's why they came up with it back in the 18th century. But disks are now thought to form around most young stars for the reasons I mentioned yesterday. The theory, the collapse of rotating molecular cloud cores, where there's too much angular momentum to have everything fall into the center, and this is the lowest gravitational energy state, consistent with the angular momentum constraint. Observations, protoplanetary disks, this shadow seen in some HST images, Beta Pictoris, the disk, remnant Dustris, the infrared spectra of young stars. And this predicts that planets should be common at least around single stars, because disks are very common. Protoplanetary disk formation and evolution. As I mentioned yesterday again, material falls down into a gravitational potential well. It gets heated. Some of that heat is radiated as it's falling in, but some is retained because eventually it gets optically thick. The photons can't get out right away, and you get a hot midplane and cooler as you go up and cooler as you go out. Material near the star falls the deepest into the potential well, releases the most gravitational potential energy, gets the hottest. And there's a lot of melting and vaporization of interstellar dust. The disk spread, it turns out that there's a lower energy state if you push angular momentum outward. And I'll just give a very quick aside to those who are physicists but not familiar with this. If you're familiar with it, you can ignore it. If you're not comfortable with physics, this is not going to be an important thing for later on. But the angular momentum, if you transfer angular momentum outward in a Keplerian potential, you need to conserve angular momentum. But the ratio of energy to angular momentum, energy goes like the square of the velocity, angular momentum goes like 1 power of the velocity, so you're going faster near the center of the Keplerian potential. And that means you have a lot more energy for a given angular momentum. Turns out it's negative energy because circular orbit, the kinetic energy is half in magnitude of potential energy. So if you take angular momentum out from the inside, put it on the outside, your energy increases, your binding energy increases net. And so if you have a dissipative process like viscosity, it tends to push material out, angular momentum outward and mass inward. So you conserve, because angular momentum is conserved, the mechanical energy, the kinetic plus potential energy, is dissipated into heat, which is radiated away. That's why disks, fundamentally why disks, astrophysical disks spread. Okay, now the biologist should wake up again. So material gets hottest near the star. The disk, if there are bumps, the profile kind of gets flatter. Most of the material falls not that far from the star, but this pushes material farther out, so it makes the big peak in density you get infall less, because a lot of that goes into the star, but its angular momentum goes out with a little bit more material.
May I ask you one thing about?
Sure.
In a protoplanetary disk, you have gases.
Yes.
This gas supports the magnetic fields.
Okay.
There is no gas, no field.
Right.
I mean, on the disk, no? Now, we know what is the minimum quantity of gas that we need to support a magnetic field that is breaking the star? Well, I don't know if this is known.
Okay, so to transfer angular momentum from the star to the disk, so the rapidly spinning star can slow down, there are two fundamental ways. If the star really is spinning extremely rapidly, it becomes triaxial, Jacobi ellipsoid. And and then it can exert a torque, gravitational torque, and transfer angular momentum that way. Otherwise, if it's going not right near breakup spin, then it's going to be flattened from a rotation, but it'll still be cylindrically symmetric, and the gravitational potential won't change. You don't have a moment arm to exert a torque on the disk. The only way you can have a disk is if you have magnetic field lines threading the inner part of the disk and to the star, and then the star is going around more rapidly. It's pulling the magnetic field and pulling the material around to try and match an angular velocity. And you don't need a lot of gas. It depends on the ionization state and various things, but it's generally, that's thought to be the major couple for the inner part of the disk to the star is this magnetic threading. And let's see, I don't have really much of a, but I can't give you a quantitative answer to
Yeah,
that.
I mean, I searched that in the literature, no answer.
Yeah. But certainly, if you get low, if gas drops down, gas close enough to be ionized and have the magnetic field drops down, then your couple starts to decrease because you start breaking the field lines.
Normally it's 10 million years, more or less.
It's
when
a-
the gas disappears
it's
and
a-
remains
yeah.
dust, only dust.
Yeah, it's actually, 10 million years is kind of the upper limit, and the typical is 1 to 3 million years.
Yeah.
Material falls in, there are outflows. The star is accreting material from the disk, and it's kind of a baby star. And if you've watched a baby eat, some things get in the mouth, and some things get flung off at very high velocity. Well, stars are similar to babies in that regard. And a lot of the angular momentum doesn't go into the disk, but it goes off into these bipolar winds that go up and down. And they're mostly polar, but they actually have a bit of an moment arm that's significantly larger, and they are very ionized. So a lot of the angular momentum goes out with them because they remain magnetically coupled to the star out to many stellar radii. And this leaves you with a disk out of which planets can form. Now, Ted talked about this somewhat yesterday, and I mentioned it a bit, that as you cool a gas, and this is more relevant for the material at 1 AU, a half AU, et cetera, that got really hot, not out at comets necessarily. You get first solids to condense, refractory oxides, aluminum and titanium oxide, and then you have some rare earths that are also, like osmia is a high temperature condensate, but it's much rarer than these lighter elements. Silicate, then you get silicates and iron, similar condensation temperatures. Which is higher actually depends on the pressure in the nebula. Then much cooler, water ice. You have some things in between, like sodium and potassium. They're the most common things in between silicates and water. Then some other ices like methane. Ammonia is actually a little higher than that. And these temperatures at which they condense depends on whether they condense as their own ices or locked as hydrates or clathrates in water ice. And hydrogen and the noble gases just don't condense. And nitrogen, if it stays in N2, even though the equilibrium at cold temperatures is NH3, ammonia, but if it stays as N2, it doesn't condense till around 20 Kelvin at solar nebula pressures. And at cold temperatures, it's very hard to have the reactions take a long time. At high temperatures, a couple thousand Kelvin, almost all the nitrogen is in N2. CO has almost all of the carbon. It's not in refractory grains. It's in the gas phase. At low temperatures, methane and ammonia are the equilibrium. Methane becomes an equilibrium at a higher temperature than ammonia, so it tends, you get more of this, because at lower temperatures, the kinetics make the reactions take longer. So that's why that and the refractory grains, carbon grains, are reasons why nitrogen is more depleted than carbon in condensed material, meteorites, comets. Equilibrium is achieved rapidly at high temperature and density, but slowly if the density, temperature and or density is small. And this is a classic plot that Ted showed yesterday about the condensation sequence in equilibrium. You actually start getting hydrated silicates, but you have to have the silicates available. This is all in equilibrium, and it's quite an approximation and assumes that everything stays well mixed and accessible. Now, physically, you have little grains condensed, or if you have individual grains merge onto one big grain, you get this fairly compact thing. But if little grains merge into 2, 3, 4, 5, 6, and then you have those things merging and growing that way, then you tend to get these clusters which are much more friable, much larger void space. This is what happens. These are computer models. This is with a size distribution, and this is with small bodies, small individual objects, or no, I guess small clusters around a core, a fairly big core. Solar nebula protoplanetary disk calculated a minimum amount of mass in the nebula by just taking the mass in the planets and augmenting it. The planets are all substantially depleted in hydrogen and helium. Augment it with enough hydrogen and helium to get to a solar composition mixture. And you get about 2%. Now, this is a minimum in the sense of you could have had a lot more and just some of the solids were lost, probably the case. You could actually have had less in the sense that material could have gone through the disk and condensed, and the grains remained in the disk, the solids remained in the disk, and the gas was removed or gradually lost from the disk. And at any one time, it never had to be greater than this minimum. But that's the minimum that made it through. The infall comes in, material hits the disk at a very high velocity, especially close in, and it shocks, it's cooled, it's slowed very fast, and therefore it doesn't have a lot of time to radiate, and a lot of energy is converted directly from kinetic energy into thermal energy. So that's why it tends to get hot. Dynamics are governed by magnetic torques, gravitational torques, viscous torques, but because of the fundamentals of mass, of conservation of mass, conservation of angular momentum, and dissipation of mechanical energy, you get material falling in to the lowest energy state for a given angular momentum. First of all, just basically constant angular momentum, comes into a disk, close as it can get, and can dissipate angular momentum that's not parallel to the symmetry axis of the disk, because material from the bottom can come in and smash into material coming in from the top of the disk, their angular momentum cancel. And then you have this spreading for the reasons I mentioned earlier when I told the biologist to get a little shut-eye, that you tend to get spreading, and material goes inward mostly, but a little bit goes outward with most of the angular momentum. Disk chemistry, I talked about equilibrium condensation and kinetic inhibition, and I suspect David's going to go into some more details, and or Ted will go into more details later on those. And then there's clearing of the gas. Disks are very common around stars less than 1 million years old. They're not very common around stars greater than 3 to 5 million years. And these disks are generally seen in dust, but the dust, if you have gas, you can't really get rid of the dust all the dust if you have gas. Because if you grind the grains, then the dust is just going to be held around by the gas. But older stars have very low mass disks, if any, and this indicates that their gas tends to be gone. And that's true where we can actually see the gas, but in many cases it's very difficult to see the gas for reasons that Ted mentioned. Now, just like eukarya have aspects of archaea and of eubacteria, the mitochondria. There are two theories that were originally independent that kind of merged to form our current basic model of planet formation. And one was the solar nebula theory. But what happened within that disk, Laplace didn't get that right at all. There was another model developed first by American geologist T.C. Chamberlain at the end of the 19th century, based on properties of rocks, that the planets formed from dust growing up to larger bodies. Collision of dust grains, and then just gradual growth into planetary-sized objects. And the extension of that for the giant planets is they became massive enough that they were able to gravitationally attract substantial quantities of hydrogen and helium because they were the most common things around. Chamberlain actually thought the disk formed from a passing star dragging material out of the sun. And that's not correct. So we've got something from Laplace and Kant and something from Chamberlain. Put them together, as Viktor Safronov did in the 50s and 60s, and you get the modern view of planetesimal theory and solar nebula for planetary growth. As I just mentioned, planets grow by pairwise accretion of solid bodies, maybe more than pairwise at certain phases, and then massive giant planets gravitationally trap the hydrogen and helium in the atmospheres. Planetesimals and condensation sequence explain the gross aspects of planetary composition versus mass. It's a general model that accounts for planets, asteroids. These are smaller, just didn't make it up to planetary size. Comets didn't make it up to planetary size and were tossed out or are in cold regions of the solar system. And moons formed in the same way. Moons around giant planets formed in the same way as planets formed around the sun. can account for the solar system, and it predicts diversity. And I'll get into that soon, as I'm going to focus on the late stage of growth, embryos to planets, because that's the clearest way to show the diversity, even for very similar initial conditions. Early stage, you have, actually, this is, sorry, micron dust grains to planetesimal growth. And that's starts with sticking forces, chemical bonding of grains to one another when they collide. That gets them up to supermeter size. Then there are various models to go from there to about 1 kilometer. And some of them are just continued sticking, and some of them are instabilities, gravitational or fluid flow within the disk. A kilometer is key because beyond a kilometer, or 10 kilometers, maybe beyond a kilometer, then gravity is the dominant force on the planet, on the planetesimals. The dominant force on everything is the gravity of the sun, but the second force is the mutual gravitational interactions of the planetesimals once they get to a kilometer or larger. And there's a middle stage, gravitationally dominated planetesimals to what's called planetary embryos, and then the late stage is the embryos to planets. Ted mentioned parts of these. Planetesimals to planetary embryos is this runaway growth where the largest bodies grow the fastest, and then the oligarchic growth where the largest body in a given region grows the fastest, but it doesn't grow as fast as slightly smaller body in a neighboring region. So you get this oligarchy where the power is divided among a small number, but not just one, of the rich getting richer. Yes?
What is the relative velocity for drawing two planetesimals to create a planetary embryos?
Okay. For forming the embryos, once we get to the planetesimals, then the collisions are typically at a little more than the escape velocity of the largest bodies, because they're the ones that are controlling the velocity dispersion, the relative velocity. And velocity relative to a circular orbit in the plane at that part of the disk. We have observational constraints, the time scales for the short-lived isotopes, disk chemistry, and interstellar grains, growth of grains sticking. As they stick, they tend to fall down towards the midplane of the disk where it's higher density and where it can become gravitationally unstable. The gas is not quite going around at Keplerian velocity. Our atmosphere doesn't go around nearly at orbital velocity. It's supported. It doesn't go down. It's pulled down by Earth's gravity, pushed up by a pressure gradient. Dense down here, less dense up there. Particles in disk are orbiting. It's their centrifugal force that balances the gravitational force. The gas in a disk, it's mostly the centrifugal force balancing the gravity, but there is this pressure gradient, so the gas doesn't need to be quite as centrifugal, so it's going a little bit slower. It's going at about 99% of the Keplerian velocity. And that means if you're dust, your grains, if you're real small dust, you just are pulled with the gas. If you're big bodies, you face a headwind. If you're big enough, so what? The density of the headwind is very low. But if you're medium size, meters, even 100 meters, you're facing a substantial headwind. that removes angular momentum from your orbit and forces your orbit to spiral inward towards the star. So things can't stay in that size range for long. They have to accrete into bigger bodies soon, or they're going to be lost. And it can, since the drag is different depending on different sizes of bodies, smaller bodies are more coupled to the gas, it can produce high velocity collisions between small particles and large particles. If the disk is flat enough, it becomes gravitationally unstable, and you get regions clumping at the planetesimals a kilometer in size or larger. But you can have a turbulence stirring things and preventing it from getting that flat, in which case they just have to have physical collisions and collide and stick to grow to kilometer size. But once you get up to kilometer size, it's mutual gravitational interactions and physical collisions among the bodies. The gas becomes just a minor perturbation. Runaway growth. We have a process called dynamical friction, which is kind of thermalization. Big bodies are moving slower relative to the circular planar orbit. They fall into the plane. The smaller bodies are moving faster. These bodies have the most gravity. They're moving at right the middle velocity, so they're easy to focus things in, and they grow the fastest. It's kind of the rich get richer, because big ones and the slow moving tend to collide the most. In this next phase, the oligarchic growth phase, the particles dominate their region, but they can't accrete one another because their relative velocity is the shear in the disk, because Keplerian orbital velocity, the sun is the big bully of the block. And so this is moving a lot faster than this, and their gravity can't bring them together. But these oligarchs each rule one region, and they accrete the smaller bodies within that region. When they get rid of these smaller bodies by accreting them, then they're starting, before that they were scattering, gravitationally perturbing one another, but they were colliding with these other bodies, they were gravitationally encountering these other bodies, and were taking away the kinetic energy, so they remained on nearly circular orbits. But once you remove the bodies, then you get, the embryos can perturb one another. And I'm going to show you some results of some simulations which started with about half the mass in 14 large embryos and 140 and the other half in 140 smaller planetesimals, nearly circular orbits. And this is between the orbit from orbit of Mercury out to a little beyond the orbit of Mars, the inner edge of the asteroid belt. It starts big, there's bigger bodies, but they're not physically this close to one another. So the mass is proportional, the radius, the mass is proportional to the cube of the radius. So think of these as constant density bodies. And these are, the bodies are actually much, much smaller than seen here, but the relative scale of the bodies is right. And we just have them gravitationally interact with each other in the sun. When they physically come within some of their radii, they collide and they accrete. And it scatters, stirs them to larger velocity. You have more growth, but things out here start getting perturbed by Jupiter and getting tossed out. And you end up with 4 nice terrestrial planets and a couple of asteroids. So, nice deterministic model. But planet formation isn't that simple. Things are chaotic. And this stage, it's very clear, very simple to show that. Because we move one of the smaller 440 bodies 1 meter ahead along its orbit. And it looks qualitatively similar, but it's different enough that we end up with two somewhat larger terrestrial planets, a little larger than Earth this time. Move that same planetesimal by 1 meter more, and now we have one planet at the end. And do it by another one, and we've got 3 planets. We usually get 3 or 4, sometimes 2, once in a while 5, once in a great while 1. But there's a lot of diversity, even with trivial changes in the initial conditions of that part of the simulation. So that's what I'm saying, you expect diversity. This is a simulation of the growth of planetesimals, from planetesimals, showing the delivery of volatiles coming in. And David's going to talk about this in more detail. Start again with a flat disk, gravitational scattering. These blue bodies, the one from colder regions, which are more water-rich, come in and they bring some water to the terrestrial planets. And this is how water-rich they are. And David has a nice movie of this, so I'll let him discuss it. This is another simulation showing the amount of material basically from different regions. And material gets mixed, but the planets that are farther out generally get more material that started farther out. But not completely. Skip this one. Mergers continue until stable configuration is reached. Fewer planets usually is more stable, even though their masses are larger because of the mergers. Resonant interactions can destabilize the system. And stable configurations better last for the lifetime of the star, otherwise they're not really stable. So planet formation will continue until you get something stable. Giant impacts and chaos imply diversity. And I just showed how trivial change in the initial conditions can lead to a large change later on. Volatiles, as Ted's mentioned, too hot to condense the volatiles in the inner solar system. Ice is condensed in the asteroid belt and beyond. Gravitational perturbations by the giant planets and by local things send volatile-rich bodies into the inner solar system. And a giant impact, which is thought to have formed the moon, would have removed most of the volatiles Earth got early on, and it would have had to accrete more volatiles later on. Most of the others would be boiled off. This takes about 100 million years, and that's kind of the date of the last big impact on Earth that resulted in the formation of the moon. This process takes longer at a greater distance from stars. So we got different theories of giant planet formation. Core nucleator decretion, big rocks, accumulated gas. Formation during collapse, planets form like stars. Gravitational instability in disk, planets form like some of the models of planetesimal formation. And this takes a little long, but it's one model, one unified model, explains the composition, motion, mass, detailed model exists. Takes millions of years. Formation during collapse, like binary stars, very rapid, but there's this brown dwarf desert. It doesn't really work. You don't have these condensations for objects that are too small. And you need a separate model for the solid bodies. It's basically this model. And there's no good model for Uranus and Neptune in this case. So people don't even think about that. You starting with a disk and having instabilities. It is rapid, but it's kind of tricky in terms of getting it to cool off enough and form the giant planets. And it requires some unphysical conditions, separate models for small bodies, and also a really good model for these intermediate Uranus and Neptune bodies. So the standard model is the core nucleated accretion, where you have this runaway growth of a big embryo of several to maybe a dozen or so Earth masses, gradual accretion of gas for a few million years. Now it's when the oligarch, basically, a giant oligarch, has accreted everything nearby. And then it's accreting gas, and as it's accreting gas, it starts to, the gas radiates away, it gets compressed, and then it accretes more gas. And once it gets about as much gas as solids, then it just starts accreting gas very rapidly. Before that, the pressure in the atmosphere prevents it from accreting more gas. Now, the planet's gravity affects the disk. It was in the art I showed about clearing gaps. And you see some gaps around some small moons in Saturn's rings. Very massive planets clear a gap, but some gas can be accreted through that. And this is just a close-up of that. This shows small planet, Earth mass, 3 times as big. You're now seeing some effects. 10 Earth masses, 30 Earth masses, 100 Earth masses, Jupiter mass. And the planet gets more and more effect on the disk as it grows. The more massive the planet is, the more gas it accretes. I don't want to spend much time on this because I want to get on to a few things. Disk-planet interactions. No gap. If the gas is embedded in if the planet's embedded in the gas, the interactions that can clear gaps also can push the planet around. The same type of interactions that push disk material inward and outward can drag the planet along, because planet masses are less than the disk mass, at least early on. And the planet can migrate. If there's no gas, it can migrate relative to the disk. If it has a gap cleared around itself, it migrates with the disk material. It's faster near the star, and that's why nobody predicted that you'd have these hot Jupiters, because people thought you might have some Jupiters that would migrate inward to the star, but why would they stop? When they were found, then there were ideas on how they could be stopped. Planet scattering, that produces, you can have motion by planets gravitationally interacting with one another. It gets very eccentric orbits, and planets, the final system planets, become very well separated, and some of the planets are ejected from the system into interstellar space. So I want to leave some time for questions, so I'm going to wrap up with these conclusions. Planet formation models are developed from data in our solar system, some extrasolar planets, observations of circumstellar disks. Planets form together with stars in the dust gas disks orbiting these young stars. And most stars do form together with such disks, which means planets should be common. Solid planets grow by pairwise accretion of small bodies. That's how the early phases of the giant planets' growth occurred, and then the giant planets became massive enough to gravitationally bring in gas soon enough for to accrete while the disk of gas was still present. We were seeing many more planets, Kepler's seeing many more planets of intermediate size close to their star Uranus, Neptune size, or maybe just 2 to 3 Earth masses, radii. And these bodies, if they're bigger than about 1.5 Earth radii, they're not big rocks, they're lower density. And if they're bigger than about 2.5 Earth radii, they definitely have a substantial amount of hydrogen and helium because they're quite low density. Substantial amount in a volumetric sense. But these things that are 3, 4 Earth radii, and in 1 AU that Kepler's finding in abundance, they have maybe a few percent, a couple percent by mass hydrogen and helium. But hydrogen and helium, that outer layer, is dominating the volume. So there are only a few to 10 or so Earth masses, but they are 20, 50 times the volume of the Earth. And if you put Earth stuff, more Earth stuff together, you put 10 Earth masses of Earth stuff together, think, well, 2 cubed is 8, so 8 Earth masses would be 2 Earth radii, and 10 Earth masses would be a little more. But that's not correct, because there's enough pressure that it gets compressed. Rocky stuff gets compressed, and therefore, actually, a 2 Earth radius Earth stuff, rocky planet, would be more massive than 10 Earth masses, about 12 or so. Planets are common, and planetary systems are very diverse. And there are new technologies, which I'll be discussing, allowing the observations of many types of planets. So with that, I'll wrap up this lecture and open the floor for questions.